So the next paper is called Sufficient Conditions for Node Expansion in Bidirectional Heuristic Search, and is going to be presented by Jingwei Chen.
Thank you for the introduction. So I'm Jingwei Chen. This is our joint work with my advisor, Dr. Nathan Sturtevant, Jurgen, Eckerle, Sandra, Zilles, and Holte. So our paper consists of two parts of one theory. The first part is for front-to-front search. The original idea for front-to-front search was proposed by Eckerle in 1994 in his thesis, but it was never published to public. Sandra and Rob worked on that part, and Nathan and I were working on front-to-end search. One day we found out that the basic idea behind our series is pretty close, so we worked together to get this paper. So this is a pure theoretical paper. In this paper, I'm not going to details of the proofs, but what I'm going to give you is a high-level overview of our theory and justification. So we know that for unidirectional search algorithms, if the state, the f cost of that state is less than c star, then such state must be expanded. But the question is, what about bidirectional algorithms? Is there any set of states must be expanded by all algorithms? So our paper answers this question. So in short, there is no single state must be expanded by all algorithms, but we can say something about pairs of states. So we will come back later. I will start with assumptions and background, and then come to our theory. The assumptions we made in our theory consists of the assumptions on heuristic search state space and the algorithms. So we assume that the state space is given as a 5-tuple of start state, goal state, cost function, successor function, and predecessor function. We denote the optimal solution of the cost of the optimal solution as C star. We require the heuristic given to the algorithm must be consistent. The major assumptions for the algorithms are the following. The first one is admissible. That is, if the algorithm is given an admissible heuristic, it should always return optimal solution, and the algorithm should be deterministic, so it cannot have any randomized method in it. And also, we require to be expansion-based and black box access to the state space, which means the only way for the algorithm to get information from the state space is through node expansion. So, unfortunately, there are some many good algorithms used in planning, such as PDL and SAS+, will not fit in our theory. So for unidirectional search, we know we have a very good algorithm, A star, what was invented in 1968 and proved to be optimal in 1985. A star uses F cost to guide the search. F cost is the sum of G cost and H cost. G cost is the current cost, and the H cost is the estimated remaining cost. So when people are talking the optimality of A star, what they really talking about, the idea is that if the heuristic is consistent, then A star is always going to do the minimum node expansion. So how do we argue that? Let's go through this example. We know that at this point, an algorithm have some state n on the open list, and it sees the f cost of n is less than c star. The question for the algorithm is that, does n have to be expanded? The answer is yes. Even if we don't expand it this time, we still find the optimal solution, we can always create another instance, and for that instance, there is an edge connecting n to the goal, and the algorithm terminates with a suboptimal solution. So the algorithm fails. So the argument is that any state must do the order states with less than C star, and A star does exactly that set of states. So if we ignore the ties, so A star is doing the minimum amount of work. So next part is bidirectional search. So the early study of bidirectional search at 1966, people are interested in bidirectional search because it has the potential to do less work. We know that the work of two smaller search can be smaller than one large search, right? There are generally two types of bidirectional search algorithms. One is called front-to-front, and one is called front-to-end. The major difference comes from the heuristic. So for the bidirectional algorithm, we have some states on the open list, and we know their g-cost. The question for the algorithm is that we want a complete path from the start to goal, so how do we estimate the remaining costs? One approach is to use one front-to-front heuristic. We directly estimate costs from any pair of nodes of the frontier. In this case, we have a edge cost function as estimating U1, V1, U1, V2, and so on and so forth. Typically, there will be n pairs of such values. An alternative way is to use front-to-end heuristic, and that is more common in bidirectional search. So we estimate the cost from a state in the forward direction to the goal, and we also have a function estimate the cost from start to a state in the backwards direction, which is called backwards heuristic. So with that background, we can come to our main contribution. So the first claim is that no single state is always being expanded. So is that true? Let's see some videos to give you some intuition. So this is a search problem on a map. So we are searching from the lower right to the upper right, upper left. So the red states are the states with f less than c star. They are expanded by should be expanded by all unidirectional algorithms, and the green states are the states that are generated but not expanded. So for the following, I'm going to pick three states that are likely to be expanded by all algorithms, but I will, for each state I pick, I will show a bidirectional algorithm that does not expand that state. So to start with, we pick some states with f less than c star in the red area. We can see that there is a bidirectional algorithm that does not expand that state. So maybe we are just unlucky. Maybe we'll try another one. So this time we pick some node on the optimal path. Okay, so we have another bidirectional algorithm. It expands different set of states. It also finds the optimal solution. We can see that this state is generated, but is still not expanded. The last one I'll try is a node closer to the still on the optimal path, but closer to the goal. We can see a very different bidirectional algorithm. Same thing happened. It generated the node on both directions, but not expanded. So we can see that for any chosen state, we seem to always can find a bidirectional algorithm that does not expand that state. So we seem to have some very bad news. Since bidirectional algorithm can behave very different from each other, they have different meeting point, they can expand different set of states. So there is no single state that is surely expanded by all algorithms. But we have some good news. The good news is that in our theory, if a pair of states they satisfy some condition, which we call sufficient condition, then at least one of them must be expanded. So before we come to our sufficient condition, we need to define F-cost in bidirectional search. So in unidirectional search, we have a term F-cost, which is the sum of G-cost and H-cost. G-cost is the current cost, and H-cost is the estimated remaining cost. So in front-to-front search, we can do the same thing. We can use the term the sum of G-cost as the current cost, and plus the front-to-front heuristic as the estimating remaining cost to get an estimate of the total past cost. With that definition, let's recall how we argue why all the states with F less than C star must be expanded. We can always create another instance. Otherwise, if the algorithm does not expand that state, then it cannot be optimal. The same argument holds for the front-to-front search. So if the algorithm says it neither expand U nor V, then it will never detect the edge connecting U or V. So we always can construct an instance too, in which the algorithm does not find the optimal solution. So a quick summary is that we have this sufficient condition for front-to-front search. I'm not going to the details of front-to-end search because we have to figure out the math here. But the idea is the same. We can always create a counterexample, and the algorithm will fail that example, and then we can argue that with our definition of LB-UV, then if we know the LB of UV is less than C star, then one of the pair must be expanded. What's good about our theory is that if we take any pair of nodes n go, where we know Fn is less than C star, we can verify that LB of n go is always going to be less than C star. According to our theory, we know that at least one of n or go must be expanded. Since go is never expanded in unidirectional search, so we know that every state n with F less than C star, such n must be expanded. Although our paper is purely theoretical, it has some immediate practical consequences. So it makes it possible to analyze the minimum node expansions for all bidirectional algorithms, which is a SOX paper. And we also build a new bidirectional algorithm upon our theory, which is called MBS. So MBS, first of all, it is an admissible algorithm, and it is the first algorithm that has guaranteed bound on necessary node expansion. It's guaranteed not to do more than twice the minimum necessary node expansion among all possible front-to-end algorithms, including A star. And you can't do any better there is no algorithm that can do any better in the worst case. So to conclude, after 30 years of having a sufficient condition for unidirectional search, we finally come up with a sufficient condition for bidirectional search. And the unidirectional sufficient condition becomes a special case of our frontier and sufficient condition. And that's all.
Questions? I have one.
Okay.
So, so you're assuming that the goal state is a single goal state.
Yeah, we assume that it's a single goal state.
Yeah. So can you say something about, doing bidirectional search when you have like multiple goal states?
So I think the problem of multiple goal states for our analysis is that when you are trying to argue some of the estimated costs, because you have multiple goal states, the cost from start to different goal states may have different costs. So the estimation is not a single value. So you cannot maybe easily create a instance to fail the algorithm. So we may derive a similar theory for that case. But
yeah. So when you do backward searching in partially specified goal,
mm-hmm.
so basically you're maintaining a subset of states, right?
Yeah, that's true.
And then you have this representation, but I guess that even though it's not the same state space,
mm-hmm.
there is some relation, right?
Okay.
I think that you can come up with a heuristic that estimate what is the distance from one guy in the front in the forward search to one node in the backward search. So I was wondering if this will apply directly.
Currently, it doesn't apply, but it may. It's possible that some small modification can be made in our theory to apply to that situation.
So, more questions? Yes.
This is a common trick, but wouldn't you be able to introduce an additional state that you then link all the goals to and have zero cost to go there? And that's how you deal with multiple goals.
Yes, that would work.
Huh?
So you introduce one more state and just have zero cost to go there from every goal.
All right.
That's your new goal, right? And then you back to the original.
Yes.
But then if you have exponentially many goals, the first
Well,
expansion will
that's
be
true.
exponentially many nodes.
So it has to be countable number of goals.
Yes. Exactly. Yes.
This is a sort of ignorant question, but it seems like bidirectional search is this idea that sort of kept coming back, and yet it was never sort of the preferred method for solving many problems, at least in a heuristic search setting. And so now, over the last few years, there's been this flurry of activity and this improved understanding of bidirectional search.
Yeah. So.
Are we closer to knowing when we should use it? Because it seems like the cases where it wins are still limited.
Yeah, so actually I come back to these slides. So we have a new algorithm, MBS. So we know that if there is no heuristic, then A star can be exponentially worse than bidirectional brute force search, right? But when you have good heuristic, then like the bidirectional search can be like times worse than A star unidirectional search. But what's good about MBS is that for any given heuristic, it's always going to be no more than twice worse than any other algorithm. So it's the first algorithm. So it has guaranteed bound on any problems. So if you are not, our recommendation is that if you are not very sure about your problem, whether it's hard or whether the heuristic is strong, then you can use MBS because that has guaranteed bound on the node expansion. So because previous bidirectional search, they don't rely on the sufficient condition, so they may doing some work that is not necessary. So That's why we cannot bound their performance, and sometimes it gets better, sometimes it gets worse, right?
One last question.
So just a clarification, you said this guarantee is no more than 2 times worse than any other algorithm, including unidirectional search?
Yeah, including A star.
So that condition, it looks pretty natural extension of the previous one, right? The condition, the sufficient condition for front to front, it looks pretty natural extension of the vector and pair condition, right?
So
it's basically the G value of one front.
Yeah.
Plus the H value of the distance from front to front, right?
Yeah.
So it's like the natural. Actually, it generalized the vector and pair condition, right?
For front to front, it's a generation of.
So how come it took 30 years to come with this?
So that's a question I'm not sure.
All right. Thank you.
Thank you.